Hello again, everyone. All right, so we've talked about some other retrieval models. We talked about cosine similarity, which has a long history, uh, not used very much, but it does have utility at times for certain things. Then BM25, which is very widely used. And now we're going to talk about language modeling. Uh, so language modeling, again, in the timeline is not the most recent, although there is a large amount, all of the deep neural nets, they deal with learning language models. And so these ideas that we have here are present in all of the very latest cutting edge approaches as well, although the models we're going to see here are nice and simple and easy to compute. So what's our core idea? What's this thing about language modeling? It's got a good name. Got to give it that. It's that the documents and anything else that with text that we have, we're going to be able to describe them with a probabilistic model that we call a language model. And so there's something about, we're going to, again, some way to describe that item in the language with probabilities. You did not see that with the cosine similarity. You didn't see that with the BM25. In each one of those, we basically end up with these notions of some sort of weight to give to the words. And you could call them, again, these sort of where each word is like a feature. And again, we're into this pattern of scoring where we take this dot product. And so we just sum stuff up and we're just trying to come up with good weights. But we don't really operate with a strong notion of a sort of a model of the document, so to speak. I mean, there is one there, right? We represent when we did cosine similarity, we have this vector space, and we've modeled the documents as vectors with these weights in them. But where do those weights come from? They're the useful weights that we find that end up with good retrieval. The BM25, there is certainly there's theory behind it, but the final result, I mean, we didn't go through the derivation, but we sort of end up at the final thing, and we see important stuff in it. These important ideas like the saturation of the term frequency. We see absolutely the importance of inverse document frequency. And there is some justification for how these are set. And we see this notion of how to treat things for longer and shorter documents in the model as well. These sort of things that we know are important to come up with in a ranking model, but they're not necessarily all grounded in great theory. Language modeling, one of its great appeals was, we'll start with pure probabilistic models, and from that we will get good ranking. And then maybe this theory that we have with probabilities will help us improve information retrieval performance. I think that's not been found to really be the case. You find yourself, these models get built, and then it's like, what can I do now? How can I make them better? And before we know it, people are tweaking things and may not be even observing the proper theory anymore, trying to get better performance. Nevertheless, I think it's a very good thing to know and to learn about, again, because lots of other techniques utilize this concept of language modelings. So let's talk about this now. So the simplest models that we can make, and these are the ones we'll use, by the way, in information retrieval, this approach, they ignore word order, okay? So they don't care whether it's good news or news good, all right? So they ignore the word order and are known as Unigram models. Now, there are language models that are not Unigram models and do pay attention to word order. We have bigram models. They pay attention to pairs of words in the order that they appear in the document. trigram, 3 words in order, and there's all sorts of other things. When we talk about speech detection, for example, and we're dealing with technologies like that, absolutely, there's this whole notion of, well, I need to pay attention to the order of the words to try to make good predictions about what is being said. Unigram, all it knows is probability of a word in this textual item. It's not going to know this word, how likely is it going to happen after a certain, I just saw this word. So there's none of that. These are the simplest models that we can make. Now, for these simple models, now the thing is they're simple, but they do end up resulting in good retrieval performance. The most popular Unigram, so there's more than one way of making them, but the most popular Unigram model uses a multinomial distribution, which means that if we take a summation over all the words in the vocabulary that we would be modeling, okay, so this is, we're going to have a sum over all words W in the vocabulary. So if we sum up these, and this is the probability of the word given the model, so it's just basically, let's go look up in the model, and model, will you tell us what your probability is for this word? Okay, this is a way to just say that. I suppose we could have written it as a function, but when we're dealing with probabilities, it's great to have a nice big capital P, and things like given, so the probability of the word given the model. All right, and they sum to 1. All right, so again, this is probability of word W given model M. Get that on the whiteboard for you. So the idea is we can go over every single word, and for that model, if we sum up all the probabilities, it'll sum to 1. So that's our notion of we're going to model our documents and other text items in this way. You can think of all of these as the parameters of the model. So with our document collections that have these large vocabularies, this means that these models have a huge number of parameters, and we need to figure out how to set them. Okay, now one thing I think the way to start thinking about things that are really helpful is that a multinomial is like a big die being singular for dice. All right, and keep in mind that these probabilities are independent. All right, so the probability of one word does not depend upon the probability of another word. All right, and it's like a die. And so, we're used to 6-sided dice that we put in our games. People who play role-playing games might be used to dice of other numbers of sides other than just 3. Of course, we're used to coins that have vocabulary of heads and tails on them, only 2 sides as well. Now, but we're talking about, you got to think of, like, it got this huge, I can't imagine how big it would be to, have 100,000, have 1,000,000 sides on it. And we could roll that die, it rolls, and then, up came the word the, with probability something. Up came the word cat. with the probability of something like that. Whatever it is that text is that we've modeled, you know, it's got some probability, let's say for the word the and cat, you know, and maybe there's some words that it has no probability for, and if we rolled the die, that side would never come up. All right, you got, so we're really starting to think about things here. This transformation where, oh yeah, we're going to be always thinking about it as this, we've got a document or we've got a query or something, you know, some piece of text, and we've broken it up into words with our regular tokenization and everything. And now we're going to model that. And we're going to have to come up with some way to set a value for every single word in that model. Okay, so what do we call that? Well, call that estimating the parameters of a model or estimation. So I pose it as a question here. Given a piece of text, how could we estimate the parameters of the model M? Now again, parameters, this is again coming up with what are the probabilities for each word in the vocabulary. All right, so we got to figure out what probability are we going to give each word to be able to model a document. All right, well, the mechanism that we use to start all of this off is going to turn out to be what, you know, when I ask this in a class, someone will usually say, oh, and they're thinking about die, and they're like, oh, we could do it like this. And I'm going to tell you the most basic way of doing this is what's known as maximum likelihood estimation. All right, and in this case, the way we're going to define this is going to go let d of w, so this is our document, and of course that's our word, be the count of word w in document D. So I guess I don't need that there. All right. So just a moment, please. All right. So then, well, if we want to, we're talking about maximum likelihood. We have to know what we mean by likelihood. We're going to, so the idea is going to be that we're going to try to come up with the values for these parameters, sorry, not these parameters, this is part of the definition, but for the parameters of the model, again, these probabilities, we're going to want to find these probabilities such that they maximize the likelihood of the data that we see in a document, okay, a piece of text. So it has these certain number of words in them, and we want to talk about setting the parameters of our model such that it would maximum the likelihood that we would have seen that data in the document. So let's define what likelihood is. So given this, we're going to say that the likelihood of our model given our data that we see in this document is equal to I'm sorry. I've got my notes are too messed up right now. All right. I'm going to fix this with looking at my other notes. Yeah, let's slow down. The likelihood of, let's just fix this. That was too many words there. Likelihood of data. And by data, we mean this is our document. So we're going to be trying to model the document. All right. Given a probabilistic multinomial model all right, is as follows. We say it's the likelihood our model M of D, that's the model of our document, given the data our document. Okay, so what's the likelihood that we have this model given the data? Where this is equal to then the probability of the data given the model, okay, which is equal to the product. So some people aren't used to the big product sign. So this isn't like the summation sign, except we're going to be multiplying. Okay. And for this, it's a product over the unique words in the document. So these are, so W is an element of D. These are the unique words in the document. All right, so those are the product of those, product of the probability of the word given the model of our document raised to the power of the number of words. So basically the idea here is, and so this is defined over the unique words, it's basically like saying, all right, we're going to go over all of the words in the document, and we're going to multiply. We're going to ask the model, what's the probability that you would have that word? And it's not that we saw that, and it's raised to the power of how many times that we saw that word. And so it's kind of like saying, well, the first word was the. Well, ask the model, what's the probability of that? Okay, so you have that probability. And then the next word was cat. And then you go, well, what's your probability for that? And we get that probability, and we multiply them together. Then the next word is. And we ask the model, what's your probability for the word is? And it gives us that probability, and we multiply that together, and we keep doing this for the whole length of the document. And so whatever that model's probabilities are, that's the likelihood that that document basically came from that model. Okay, so this is what we're trying, this is how we define what the likelihood of data is. So when we see this text data and we've got the multinomial model, this is how we calculate the likelihood of this data given that model. Our goal with maximum likelihood estimation, though, is to say, all right, yeah, I've got a document, I've got this data, I can go over the words in it, and I know its word counts. Now, what I want to do is I want to come up with these weights which will maximize this. All right, so that's what maximum likelihood estimation is. It's coming up, it's setting what the parameters are, which is this, the model here, which will maximize this product. All right, well, it turns out, so I'll write that on the board, on my little whiteboard, and just pose that as a question. It's basically what parameter settings of the model, this is MD, maximize the likelihood for the, what we could say is the data in the document. All right. Now, I could try to work through the solution for you and how do we get there, but I'm not going to. We're going to skip to the answer because the solution to this question is as follows. So we'll write the probability. When we want to be clear about where our probabilities came from and how we estimated them, we can say this is the probability with a maximum likelihood estimate for a word given the model of the document happens to be equal to sort of what might be obvious is we take the count of the word and we divide it by the number of not unique words, but by the total number of word occurrences. So this is the document length. So we divide it by the document length. Okay. You know, makes kind of sense. This is what seems clear. Oh, okay. Well, I saw the word the, 20 out of 100 times. So the probability that I have the word the in that document is 0.2. It made up 20% of the word occurrences. So I'm going to say the probability is 0.2. That's what maximum likelihood estimation turns out to produce for the model. Okay. So the great thing is about this is this tells us we have now an easy way, or at least a first step to how we could estimate and come up with models of text. All right, so basically now we can make models of text, which is great. This is, of course, not going to be the end of the story about making models of text. One of the great notions in the language modeling approach to information retrieval is, so again, we decide on what our model is. Our model is this multinomial. Okay, so a document will have a probability for every word in the vocabulary. Again, it's like a gigantic die. And then, but we could invent other ways and other methods of coming up with these probabilities other than the maximum likelihood estimated version. Just to foreshadow, we could think about, the reality is that, we might want to say, for example, for some documents that, let's say we have a document that talks a lot about gasoline, but it never uses the word petrol. We might want to say that there's some probability for the word petrol in there, even though maximum likelihood estimation would say, well, it's the probability of petrol? 0. But we know from a language usage and language meaning standpoint that petrol and gasoline are basically the same thing. So does it make sense to model what a document means with only the words in it? Or could we end up with better way to estimate its probabilities if we did something smart and we gave some probability for a document that has the word gasoline in it also to the word petrol? Perhaps. This is where a lot of this sort of research has looked into over the years of, like, again, how could we come up with a better way of setting these probabilities? How could we better estimate the probabilities of this language model such that then when we use those probabilities in our retrieval system, that we actually end up with improving our retrieval quality? We're better able to rank those documents. All right, so that's the first part of this. I'm going to stop the video and then start it back up, and we'll continue on.